Okay, in this video we're going to look at finding the derivatives of exponential functions. And our first special exponential function is the function e to the x. Remember, our base e is not a variable, e is a number. It's about 2.718. It's an irrational number, very similar to pi. So the derivative of e to the x is e to the x. So remember, e for easy. Okay, it's easy because you get the same thing back. Now technically here we have x as our power. We're really chaining along the derivative of x, which is 1, but we don't bother to write that. So what we have to keep in mind is if we are finding the derivative of e to any function, alright, see, most of the time it's not just going to be e to the x. It's going to be e to the x squared plus 5, or whatever the function may be. We have to know that the derivative of e to some function, yes, it's e for easy, you get the same thing back, but the chain rule is in effect here, where we're going to have to chain along the derivative of that power. Okay, so quick example. Okay, suppose we wish to find the derivative of e to the x cubed. So e for easy means we get the same thing back, but don't forget we have to chain along the derivative of the inside, and the inside is the power for this particular function. So the derivative of x to the third is 3x squared. If this is multiple choice, you're likely to see it written like this. Okay, so this would be our final answer. One more example here, y equals e to the 5x. We're looking to find our derivative. If it's linear for the power, we know the derivative of that is going to be just the number in front of x, so 5. So we put that in front, and then e for easy, we get the same thing back. Okay? So our special case of e to the x really followed this template here. The derivative of some constant, which if we call that a, is really equal to that same thing back. Remember we said e for easy, so in this case it's a to the x, same thing back. And then in our case of e to the x, we really are taking the natural log of e, and the natural log of e is just 1. So that's why when we looked at the derivative of e to the x, we got e to the x times the natural log of e. Well, again, this piece is 1, so that's why we were left with just e to the x. So why do I show you this? Well, you're not always going to have a nice base of e. Suppose we wish to take the derivative of 3 to the x. Okay, so remember we said e is about 2.718. Okay, so it represents a number. So what if we have a different number, such as 3? So you get the same thing back, just like we saw you get the same thing back with e to the x. But the difference here is we now have the natural log of our base, which is 3. And like before, we're chaining along the derivative of our power, which in this case would be 1. Okay? So if we were to generalize here a little bit, excuse me, if we were to take the derivative of a to some function, call it f of x, because again it's not usually just going to be a plain x, we're going to get the same thing back, so a raised to that function times the natural log of the base, which in this case would be a, and then we have to chain along the derivative of the power, which would be f prime of x. So let's look at another example. Okay, suppose we wish to find the derivative of 4 raised to the 3x squared. Okay, so we have a constant raised to a variable power. Okay, that's really what we're doing here. Let's jot that down. Okay, so really what this formula here is showing us is it's when we are looking to find the derivative of a constant raised to a variable power. Again, our constant is what we're calling a. So in my example here, my constant is 4. Okay, it's the base. So we are going to get the same thing back. So 4 raised to the 3x squared. It's always going to be times the natural log of the base, and then you're going to chain along the derivative of your power, which in this case would be 6x. There's nothing we can do to simplify this, so this would be our final answer. The only thing you could possibly do is rearrange the order of these terms, but that's it.